very beginning of recording in progress. Got it. So here you see the very beginning of the famous Middle English text of Beowulf, and I'll try to pronounce this. What we hardena in heardahum theod kninge thrym gefrunon, something like that. And it's almost unrecognizable. But then you get to Middle English, which is basically between the Norman conquest and the colonial period. And now with a little bit of work, you can read this. Here is a little bit from the beginning, or well, from part of the Canterbury Tales. Waping on dweiling, care and other sorwe, I know enough on even and amorwe, quod the marchant. So something like that. There's a vowel shift that happens, which is why some of the pronunciation feels a little bit different, but with a few footnotes, we can kind of read Middle English. And then we get to Shakespeare and the colonial period, and it's pretty much readable as modern English. So there's a couple of interesting things going on here. For one thing, English has changed a lot over the centuries. Not all languages do this. Oddly enough, Icelandic is apparently very stable, and people who speak modern Icelandic can apparently almost read Old English. Sometimes these language changes happen for an observable reason. So between Old English and Middle English, we have the Norman conquest. There were some changes in Old English that are attributed to contact with Old Norse and other languages as various settlers arrived on the British Isles. But then the big change at the Norman conquest, of course, is that the French invaded England essentially, and now you have this huge political upheaval, lots of contact with the French as it was spoken at the time, and so a lot of changes in Middle English are associated with that kind of language contact. There is, however, an interesting one that sort of defies explanation, and this has to do with something called verb raising syntax. So in Middle English, you could raise a main verb and invert it to form a question, like, know you what time it is? And you could also raise it to above a negation word and say, I know not what time it is. And we can understand that in modern English, but you have to try really hard to get yourself to say it. It's very unnatural. In modern English, we instead use something called do support, which is that we insert the auxiliary verb do and raise that instead. So do you know what time it is? And I do not know what time it is. A couple of interesting things about this change is that it seems to have happened for no particular reason. There are some hypotheses about how it got started, but nothing definite, and no political upheaval, for example, that might have triggered this change. Here's some data from manuscripts. So to explain kind of where this came from, there was a linguist, Elgard, that worked on this and went through a bunch of Middle English manuscripts and looked at sentences that could either show verb raising syntax or do support syntax, and just counted how many of each kind there were. And then you divide the manuscripts up into time and just plot the fraction of sentences with do support out of all possible sentences of that type. And so, for example, this is dealing with a particular kind of question. And you can see that here in around 1300, there is essentially no do support, but by the time you get to the late colonial period, there's almost exclusively do support. And then in between, you have this sort of transitional period. And what you see here, this curve, that's a exponential sigmoid plotted just with logistic regression. So one interesting thing, as I said, is that there doesn't seem to be any particular reason why this syntactic change took place. And the second thing is that it started and ran to completion. That seems to be typical of language changes, not just syntactic ones, but also changes in pronunciation and so on. And in the few cases where there does seem to be a change that sort of gets started and then reverts, there's some explanation for why that happened. So the goal of this particular project was to see if we could figure out a mathematical model that allows for spontaneous language change sort of the correct type on the correct time scale, and just sort of see what mechanisms are required to make that work. So human languages are stable on long time scales, but can change spontaneously. So as I said, English had verb raising syntax for many, many centuries. And then in the course of just a couple hundred years, it changed completely. So what might be the forces causing this sort of thing to happen? So first force is regularization. And this is related to the concept of regularization in data science, which is the ability for a learning process to sort of ignore noise. Children are able to discard noise in the primary linguistic data that they learn from. So if you have a few sentences with some ums or some sort of incomplete structure, children are able to cope with that intelligently and don't conclude that you have to put an in the middle of every sentence, for example. This is something that stabilizes language, because if something starts to creep in that's uh, an unusual construction, children might just ignore it as noise, and then uh, it never really takes hold in the language as a whole. So this is a stabilizing force. But children also do something called incrementation. They detect and amplify correlations between language variation and age and social status. And this is something that's easiest to see in the phonetics literature, because what you'll have is, say, you can put vowels in sort of a two-dimensional map, and what you'll have is that, say, one generation places their ah sound here, and then the next generation places their ah sound more there. Well, children will sort of interpolate and figure out some place where it looks like the population is going and target their speech pattern toward the prediction, it seems, rather than the actual present state of the population. It's a little bit weird. The easiest one that I've come up with to sort of explain this is that if your grandparents talk a particular way and your parents talk a particular way, and there's a systematic difference, then maybe the children don't want to sound outdated. And so they don't want to use constructions that their grandparents used, but their parents don't. Or if there's something that their parents say that their grandparents didn't say, maybe they think that's where the population is going toward, and they'll use it even more than their parents did. So this is kind of a destabilizing effect that can add a sort of momentum to a language change once it gets started. So I'm now going to show how to build up a model step by step. So for the first step of the model, I'm going to just focus on regularization and stability. I'm going to suppose that there are two idealized grammars, G1 and G2, and you can think of these as the raising syntax, as in know you what time it is, and maybe do support syntax, do you know what time it is. Let's assume for the moment that the population is well mixed and that what children are learning from is just, out of all possible sentences where you could tell whether the speaker is using G2 or G1, what is the usage rate of G2 across the whole population? So that's what this M is. Then we need a learning function, which says that if you've got children who are learning from an environment where the mean usage rate of G2 is M, what is their mean usage rate as a result? And that's this learning function Q of M that I'll display in a moment. So then you set up a fairly straightforward differential equation here. This is a birth and learning term, and then there's a death term. You set the birth rate equal to the death rate so that the population size is in equilibrium, and you change time variables, or you change units on the time variable to make that birth and death rate equal to 1, and that's where this differential equation comes from. More formally, you can derive it from a Markov chain, and I'll say more about that later. But this is the core idea. So if we want a population to have two stable states, one where everybody mostly uses G1 and one where everybody mostly uses G2, that means we need this kind of phase portrait. So since M is a usage rate, it's between 0 and 1, so the phase space is a closed interval, and there should be a stable equilibrium on the left and a stable equilibrium on the right. They should be fairly close to the endpoints of the interval, and because of the geometry of dynamical systems, there has to be this unstable equilibrium in the middle. So that sort of gives us the base case that you could have stable Middle English with verb raising and stable Modern English with do support. But now, so before I get into the transition, I want to show you what that tells us about this learning function. So here I've drawn a specific learning function. It's a cubic polynomial that I just sort of concocted, and it has the important feature that Q of M minus M is 0 right there and right there. So those are the two stable equilibrium points. And then there's an unstable equilibrium point in the middle right there. The area here means that if the population as a whole uses G2 a lot, then the children will use it even more. And if they don't use G2 very often, then the children will use it even less. So this is an aspect of regularization, that if a form seems to be falling out of use it less. So what we'd now like to do is say, is it possible for there to be a spontaneous change from one of these equilibrium states to the other? Now, just within this deterministic dynamical system, that's not possible. So we have to add some kind of random fluctuations. And to do that, I'm using a modification of a model that comes from the population genetics literature, the Wright-Fisher process. And I'll say more about that later in the slideshow. But it transforms this deterministic differential equation into this stochastic differential equation. So I've replaced the M with Xi. The drift term here matches the deterministic vector field that we had before. Then this is a Brownian motion, and this is just the size of the fluctuations. Now, the epsilon is, as you would expect, a small magnitude positive number. The business with the square root of Xi times 1 minus Xi has to do with the phase space. So since the phase space is a closed interval, we don't want to allow a population here to be able to sort of escape into negative territory, and we don't want it to escape into greater than 1 territory as well. So when you draw this thing, you get a semicircle, and the noise hits 0 at the boundaries, and it goes to 0 fast enough at the boundaries that it prevents random noise from being able to take the population outside the interval. So that's something that's, for one thing, it comes out of the Markov chain, but it also it's also necessary for well-posedness of this stochastic differential equation. So now the question is, if we do put in that kind of noise, can the population sort of wander around over here for a while and then wander across the middle and keep going and end up over here for a while? Well, it turns out that there is something called large deviation theory that lets us learn something about the time scale on which the random fluctuations could cause a change like that. That's something called noise-induced transition. And unfortunately, when you do the calculation, you end up with an expected value of the transition time that is many orders of magnitude greater than the age of the known universe, it just doesn't happen. And it should be clear why, going back to this slide, the random fluctuations would have to push the population contrary to the vector field over quite a distance. And getting all of those random fluctuations to cooperate to that extent is just unbelievably unlikely. So eventually it will happen, but not on the correct historical time scale. So we have to move on to something else. And so this is where we need to introduce incrementation. So with this, I'm going to take advantage of the fact that children can detect and amplify trends and divide the population now into two generations. So I'm going to let Xi be the mean speech of the young generation and zeta be the mean speech of the old generation, and define a prediction function, R, that indicates where the children will predict the population will be in the future. To make it, just to come up with something reasonable, I started with putting the unit interval vertically, and I'm using a exponential sigmoid to map the whole real line up to that unit interval. I look at where zeta and xi are here. I map them over to the t-axis, and then just continue the trend over to the left or to the right, and then map that number back up to the closed interval. And so that's the rate that children are predicting later. I have a specific one of these in mind. You know, you can see here I'm using 3 for this distance and so on. But it, the geometry is such that I think you have a lot of flexibility on what these functions look like. But just to be definite, that's where all the numerical examples come from. Okay. When you write down the deterministic part of the dynamics, it's now got two differential equations. This first is a birth and learning term, but children are learning from where they predict the population will be rather than where it currently is. Then there's an aging process that moves mass from the young generation to the old generation, and a death process that removes some of the old generation. And again, I've normalized the population size and set the time scale so that the birth and death rates are both 1. Okay, so when you look at this vector field, this is what you get. Again, there's a stable equilibrium here and another stable equilibrium there. Those are where the population as a whole strongly prefers G1 or G2. There's a basin of attraction for each of these stable equilibrium points. And their shape is very interesting because all of this is the boundary of that stable state. And then all of this is the basin for that state. And the boundary between them is generated by this saddle point in the middle. And the green dotted line you see there is the stable manifold of the saddle. It's kind of hard to see with the arrows, but that really is the stable manifold of that saddle point. And so what that means is that if you were to somehow start a population right on there, it would move indecisively towards the saddle rather than towards either of the two stable points. And if you zoom in, so let me zoom in down here, what you see is that the equilibrium point in the lower left corner is actually very close to the boundary of its basin. And the same holds for the stable equilibrium up there. So this is something that we couldn't do in one dimension, because in one dimension, the two fixed points had to be at a great distance away from the boundary. But here they can actually be very close to it because we're in 2 dimensions. So now, if you imagine trying to get a noise-induced transition, if you put some random noise into this, eventually the population will stray across that boundary. and then the vector field will sweep it up to the other equilibrium, where it'll kind of hover for a little while until it strays far enough across the boundary, and then it'll go back. Intuitively, what happens in this kind of transition is, let me do it here, is that by some accident, you'll see that the positions of the old generation and the new generation indicate some kind of trend. Actually, that's not a good thing here. So the young generation and the old generation, there will be some kind of trend, and children will sort of amplify that trend. And so yeah, let me draw it like this. So this is just a chance correlation between speech and age, but children don't know that it's just an accident, and so they amplify this, and that starts to push the population, and now it'll drift across the boundary and be swept up and make that noise-induced transition. So this is what I mean when I say prediction-driven instability, that you get this noise-induced transition, and it happens because a prediction picks up on just a chance correlation and amplifies it. Well, when you go back and add that random fluctuation to the model, in the easy two-dimensional case, this is the system of stochastic differential equations that you get. So again, the vector field shows up here, and you get straightforward fluctuation terms like what we were seeing before. And again, there's this epsilon, and I'll say more about the epsilon, where it comes from. So now the question is, does our intuition work, and does this actually have the right properties? Do we get noise-induced transitions on some sort of reasonable time scale? Well, to do that calculation, I'm using something called large deviation theory. And this is something from there's sort of a classic book by Friedland and Wenzel that I'll show you later that sort of goes through this. For a general stochastic differential equation, you define something called the normalized action functional. And what it says is, suppose that f is a path over time through phase space. I look at f prime at a particular time and compare it to the vector field at the value of f at that particular time, and then just see how well they agree. And the a subscript there is just that you sort of scale, you weight the different parts of the phase space by the size of the noise. And intuitively, this measures how strongly the path f flows against the vector field. So if f is actually a solution to the vector field, then f prime will equal b of f of t, and all of this will total 0. But if it flows against the vector field, then it is accumulating some sort of cost. This is called an action functional because it's closely related to Lagrangian mechanics. So you can think of this as being a Lagrangian density. And that gives us some tools to work with. So having defined the action functional, the quasi-potential is that, okay, you start with a fixed point x1 and you start with a fixed point x2, and you look at all paths that start at x1 and end at x2 and compute the action over that path. And then you look for the infimum over all possible paths. So you're looking for a path of minimum action. You're looking for sort of the minimum effort. What is the least that you have to go against the vector field in order to get from x1 to x2? And that's the classic book where all of this is figured out. then once you've got the quasi-potential between the two fixed points, through some complicated and difficult probability theory, you can estimate that if tau is the time until the next random transition, that the expected value of tau is approximately e to the power of 1 over epsilon squared times the quasi-potential v. So intuitively, it's dominated by the path, the escape path of least effort. The bigger the noise, the easier it will be to escape from one fixed point to the other. And so for larger values of epsilon, this is a smaller number, and so its exponential is smaller. Also, it should be clear that if the quasi-potential v is at all large, you're going to end up with exp of a very large number when you divide by epsilon squared. And so this is why for the one-dimensional case, we were getting those just tremendously huge numbers. It's because the only path from x1 to x2 has to go over this area. And so you're accumulating a lot of energy in that action right here. And so you end up with a large number v right there. But since we have 2 dimensions and we have a boundary that's very close to the fixed points, it looks like it might be possible to have a least action path that looks something like this. So you start at x1 and accumulate a small amount of action there because you have to go contrary to the vector field. But then once you're across the boundary, the path can just follow the vector field and there's no contribution to the action integral. So there's only a very small part of the path that's actually contributing to that action integral. Okay, so the theory is one thing. The numerics is something else. So here's what I was able to come up with after actually several weeks of trying a bunch of different numerical methods and things. And it's hard to see until you zoom in. But this is a path that starts at everybody using grammar 1, and then it eases through the basin boundary, and then it follows the vector field, and then it comes up here to the other fixed point. Couple of things about this path that I should say. First is that I don't really believe this part of it. If you look, this fixed point is a spiral, and so it really, the solution ought to spiral in, something like that. And it's just that the numerical method that I ended up with is not able to figure that out. So it ends up giving too large of a number for the action and the quasi-potential. And I think the same thing happens down here. I think that there really should be some spiraling out that, again, the numerical method just can't capture. And I've tried all sorts of different things, and I'm just not sure how to make it work. So let me say a little bit about this numerical method. So first, I pick a finishing time t, and eventually I will increase t and see what happens, because you should be able to do this over t going off to infinity, which is not computationally possible, but we can at least see what happens. So I was doing this in Mathematica, and it has some sort of peculiar features. You can actually define a piecewise polynomial spline as something called an interpolating function, but you can do it with unknown symbolic values. So you can tell it, give a symbolic value for various points on a curve and also derivatives at those points, and leave those as unknown symbolic values rather than having to put in actual numbers. Mathematica's built-in integrate function can actually take an interpolating function in that symbolic form and construct a huge expression for the action integral S. Along the way, you ignore various error messages that seem to be harmless and are mostly Mathematica complaining about how it can't evaluate things all the way down. You then start with an initial guess at the path and then use kind of a generic symbolic minimization function to try to solve for all of these unknown symbolic values. And then you put it back together and now you've got the approximate path. It works reasonably well. This is what actually came out. This part is where the path is just starting to leave the fixed point. Then I believe this is where it crosses that basin boundary, the stable manifold of the saddle. Then this is where it's following the vector field. And then this is the part that I don't believe. This is where it kind of slides over to the second fixed point instead of spiraling in. So basically, I just sort of don't believe that part of it. But I think this part is at least vaguely correct. And when you do that, so I'll just chop all of that off and integrate up to 5, you do get a small value for S. And with epsilon equal to 0.02, you end up with an expected value for the transition time that's only 2.78. And given that the time scale here is sort of the lifespan of an individual, this is now in, say, 2 or 3 generations. And so now that's on a century time scale. So this is now giving us, it's not numbers that I would expect to actually apply to any particular set of data, but it's at least the right order of magnitude. So, as I said, I've got a Markov chain going on under the hood, and I can actually run samples of that Markov chain and see what they look like. And this is a sample run of the Markov chain, plotted again with the young generation here and the old generation there. And if I zoom in here, you can see that from the initial condition there, the population just kind of wanders down to that fixed point. It wanders around there for a while until a transition happens. Then it follows with some noise the vector field up to this other fixed point. It hovers around that for a while. And then there's a reverse transition. And that's what you see here. And in the zoomed in part, this is the reverse transition. Okay, so this is now a mathematical model that is at least giving qualitatively reasonable results. There was one last feature of the do support data that I was a little bit worried about, and I won't try to page all the way back there, but it was giving us something that reasonably fit an exponential sigmoid. And one of the things that I was sort of concerned about is that if you look at the speech pattern of the young generation, which is the blue curve here, it seems to sort of do this. So the takeoff here seems to be sharper than the data would suggest. And it's not just the do support data. There are a lot of language changes that have that nice sigmoid shape. But then I realized I was only looking at the young generation. If you look at the old generation, which is in orange here, that shows a much softer takeoff. And so that's another qualitative bit of agreement with the linguistic data. You can also see down here that I've adjusted the time scale to be in years. So you can see that the time between transitions is a few centuries, which seems reasonable. And the actual time of transition is on the order of a century, maybe a little less, which also seems reasonable. So again, we've gone from something that was clearly the wrong time scale to something that is much more in agreement with our data. So now I want to give you a little bit of information about the Markov chain because it has, there's one odd little feature of the Markov chain that turns out to be really important. So here's how the Markov chain is set up. I divide the population into an old generation and a young generation. They're both of size big N, and I discretize the unit interval so that people in this pile use all G1, and people in this pile use G all G2, and then the ones in the middle use some mixture. And the mixture is sort of the obvious thing that you use it, say, 1/6 of the time or 2/6 of the time. Are these fifths or sixths? I think I used sixths for my picture and fifths for my uh, for my actual numerics. Oh well, but yeah, so you get the idea: 0, 1, 6, 2, 6, 3, 6, and so to 6/6. Um, the aging process is that you imagine someone from the old generation being removed, and then you resample the young generation. You sample from the young generation to get a replacement. It's easier to make the math work out when you do it that way, as opposed to actually moving an individual from one generation to the next. Um, I don't think there's any significant consequences to that simplification. It just makes the theory somewhat easier. Um, then for birth and learning, again, you sort of remove someone from the young generation, and actually that X is in the wrong place. That should be right there, and replace them with a child generation. The way that works is you compute the mean speech pattern of the old generation and the young generation. You apply that prediction function R to see where the population is going. You then construct a binomial distribution that has the right number of possible outcomes and whose mean agrees with the mean from that prediction function. You sample from this distribution, and that's how you tell where to put the new individual in the young generation. There's a couple of other tiny details that I don't want to get into that have to do with making sure everything is well posed. But that's the gist of the birth and learning process. There's also this resampling process. What this says is that each individual has a certain probability of just copying the speech pattern of someone else from their generation. And this is something that is sort of the main driving force in the population genetics model that I'm basing this on. With the population genetics model, you imagine that an individual dies and you replace it by cloning one of the other individuals. Here, what you're imagining is that a person just decides, perhaps subconsciously, that they're going to speak a different way. It's maybe a surprise, but this is actually something that happens in real life. One of the peculiar observations that linguists have come across is that adult men tend to talk like their mothers, and adult women tend to talk like their friends. So women are sort of more eager to adapt their speech pattern to their peer group, and it is thought that that force is really key in getting language changes to happen. And again, that it's most noticed. I've seen it the most in the phonetics literature, but it seems to also happen in other parts of language. So as sort of bizarre as this resampling step seems to be, there is actually real evidence that this happens. And the reason that this is important is that the epsilon here depends on the resampling rate. And if you set the resampling rate to 0, then the epsilon goes to 0. And that wipes out the noise terms, at which point you no longer have noise-induced transitions. And so again, the thing that's happening going from the Markov chain to here is that you take the limit as the population size goes off to infinity, and the fluctuations have this factor in front that depends on the resampling rate. And that resampling rate vanishes in the limit if you don't have that resampling strictly greater than 0. So let me state, before I run out of time, state some conclusions. So the goal was to create a model of population dynamics with learning um, based on the history of English and a lot of other languages. We want two stable fixed points, each dominated by sort of the older idealized grammar and the other by the newer idealized grammar. And we wanted to see if there was a way to have a noise-induced transition, so just a spontaneous change from one grammar to the other. And if you try to do this without age groups and incrementation, then you're limited to one-dimensional dynamics, and the transition time is many orders of magnitude too large. But with age groups and incrementation, you get this prediction-driven instability effect. The dynamics are now two-dimensional, so the fixed points can be close to the boundaries of their basins of attraction. And when you apply large deviation theory, it looks like we're getting reasonable timescales for these transitions, for how long they take and also how long in between the transitions we go. And a detail from working out the Markov chain is that random variation in adult speech turns out to be necessary. So with that, let me just show you this page of references in case you're interested in learning more about this. So first, this is a fairly old article that goes over the collection of the Middle English data. This is a newer article by Anthony Kroc at the University of Pennsylvania. He's a well-known linguist, and he was doing a lot of statistical analysis. And this paper is basically that in the case of do support, for different kinds of sentences, you see transitions that happen at slightly later or earlier times, but there's statistical evidence that the shapes of these curves are all the same. And that pattern seems to hold in other languages with these changes that affect several different kinds of sentences as well. So that's this article. This book has the Wright-Fisher process and the convergence of Markov chains to stochastic differential equations in the way that I needed. This is the noise-induced transitions work. This was a newer paper that had some other numerical methods for large deviation theory. And I tried several of those numerical methods and was just not able to get them to work. And then this is my article that goes through all of the gory details of the convergence of that Markov chain to the stochastic differential equation, proving everything is well posed and converges properly. And there's a lot of sausage that has to get made to confirm all of that. So that's what's in that article. Since we have just a couple of minutes left, I do want to show you a little bit more about the Markov chain. So as I said, we have two generations, young and old. We discretize the usage rates, and we keep track of the overall usage rate of the population. And you have to do these scalings. So you define a death and aging rate that's so many deaths per unit time. And then you set up a probability where you divide by the generation size. And a time step has to be 1 over n years, where n is the generation size. And so that's how you connect the parameters of the Markov chain back to actual time. This is how you set up the learning generation. It's, as I said, a binomial distribution that's set up so that its mean is the desired result. And for the resampling, there's again a resampling rate that's scaled by the number of, by the population size. And this is what I did to get all of those numerical examples. And the sort of punchline is that this is the expression for epsilon. And you can see right there, there's the resampling rate. And if that ends up being 0, then epsilon is 0. And so that's why you need that resampling process to make sure that the noise-induced transitions are actually possible in the limit of an infinite population size. So with that, I think I'll stop and see if you have any questions.
All right, I'd like for us to thank our speaker. You're going to see there's a bunch of emojis on the Zoom screen as well. Right. And do we have any questions for our speaker?
Can I ask one, Kristen? Or sorry, I think Terry has his hand up. Sorry. I'll let Terry go first.
Please go ahead.
Oh, okay. Garrett, I was sort of wondering, so when I look at this, right, there's sort of this switching right back and forth between these two stable equilibria, right? I mean, you sort of, and so you sort of start to approach, and then the noise term bumps you off that equilibrium, eventually across into the other basin of attraction, you go back. So thinking about this back in the context of sort of, I've forgotten the linguistic terms, but the do support and the other
verb raising.
And verb raising. So would this suggest that like we're due to come back to verb raising at some time? And if so, do we know, are there observed instances of this like cyclical back and forth sort of behavior, or?
Yes and no. So for one thing, this is all in the case where there are only two possible idealized grammars. In the case of a natural language, there are many possible idealized grammars. And so what's likely to happen is that we'll have a transition to a different one rather than going back to the one that we came from. And I've set up models that do that. It's just they're harder to draw. There are actually some cyclic structures in language change. There's one that I believe this is called the Jespersen cycle. And it has, I think that's the right one. And it has to do with where you put negation, because in French, it's easier to see, because right now in French, there's a two-part negation. So you put a ne and a pas on either side of the verb with some complications. But what's happening is that French speakers are sort of leaving off the ne. So that gives us a one-part negation. But then you start needing emphasis. So there's just, I do not like ranch dressing. But then there's I do not like ranch dressing at all. So you get these emphasis. So you would end up with sort of a negation and then a more emphatic negation. And then you end up sort of transitioning back to some kind of two-part negation construction. And something like this apparently happened in English as well. I think I'm not as familiar with it, and I think it's maybe not as clean, not as easy to see. But actually, the pas that you see in French is an emphatic word that was added sometime in the distant past. So there are cycles in the grammar space. As far as the specific transition that I talked about in English, one of the weird things about English is this do support syntax. As far as I know, English is the only known language that uses it. There's some hint of it in Dutch and Korean, I think, but I don't think any other language has truly adopted do support. so it's sort of hard to say what happens when you have a language that changes back.
Right. Great. Thank you very much.
Terry, would you like to ask your question?
Sure. Has Stephen Strogatz done any work in languages?
Actually, he did. There's a paper by Strogatz and Danny Abrams, and it's about how it's about language death. So very often you'll have situations where there's a population that speaks multiple languages or maybe even multiple distinct dialects. And depending on whether the minority dialect is seen favorably or unfavorably, it might go extinct. And so they had an article about language extinction in that case.
Okay, thank you.
Yeah, there's also a model by Smale from a few years ago, but it has this sort of unfortunate property that if it's about how if everybody sort of learns from the mean and aims toward the mean, then you end up with a very stable population that never changes its language. And so it's kind of missing the dynamical ingredient that I was trying to capture here.
So Garrett, sorry, as a follow-up to that, I'm just wondering, so has anyone ever looked at, I mean, right, obviously the close proximity of the equilibrium to the boundary of the basin of attraction provides some sort of, I mean, provides an advantage or encourages the language to change in some sense, makes it more likely. Has anyone ever looked at that? I mean, it's from sort of an evolutionary perspective in terms of like the likelihood of language surviving based on these sorts of features. I mean, and obviously natural language is much more complicated than this, but I'm just wondering if you have any thoughts on that or know of anyone who's looked from that perspective.
So do you mean as in on biological evolutionary timescales or historical timescales?
Like biological.
And so are you?
So let me try and formulate my question a little better. Like if I compared sort of two languages and I wanted to know sort of what's the likelihood that this language, based on some certain features of that language, what's the likelihood that this language sort of might be adaptable. I'm not making this very precise, but like somehow I'm just wondering if are there other cases, right, where this you don't get this switching and you can see that that's precisely because things aren't close to the boundary.
Yeah, so so let me see here. What can I say about this? I mean, page. So a lot of times you'll see language changes where a change in the syntax is connected to a change in morphology, which is connected to a change in phonetics. So one of the big things that happened in English was that our rich morphology vanished. So if you go back to Old English, all of the verbs had different endings for different subject pronouns, and nouns were also declined for case. So there was rich case marking, and phonetic processes tend to sort of reduce those endings. And once those morphological features sort of fall out of use, then that frees up the syntax to start changing, because now there are things that can be interpreted in multiple ways. And one possibility, I'm speculating a little bit here. I don't know how much this has been done, but if you have a significant number of adults speaking the dominant language as a second language, those morphological details are things that they tend to sort of gloss over and forget and not do quite right. And if children are mistakenly learning from that, then they can sort of incorporate, they sort of will say that, okay, there's noise in how you put verb endings on, and they'll simplify the language so that it doesn't have those anymore. So if you look at the history of English, originally Old English was very much like Old Norse. And what seems to have happened was it wasn't the language so much, it was the environment. That within the British Isles, there were several closely related languages. And it seems that the contact between those languages may have confused the children and eventually led to a simplification of the morphology and syntax. Whereas Old Norse, especially when it was taken to Iceland, was more isolated. And so there was sort of less confusion about that sort of thing. I don't know if that's an answer to your question. So it's to some extent it's the language and how vulnerable it is to phonetic reduction and changes to morphology. But also the environment.
Yeah, no, I think your example of sort of you have these phonetic things that then that give some reduction, and then the syntax now allows for more. That's exactly sort of the kind of example I was wondering if you could have this. And I think yes, I understand now. Thank you.
Yeah, and I wish I knew more about Asian languages, because Mandarin and Japanese both have very minimal agreement morphology. I mean, really, they don't have any. And that suggests that something like the history of some things that happened in the history of English may have happened to Chinese and Japanese as well, but I don't know enough about the histories of those languages to really say.
All right, you want to be respectful of everyone's time. It's just over 4 o'clock. So can we thank the speaker one more time? And if anybody else wants to stay after and to ask questions, they can, but let's thank the speaker one more time.
Okay. Well, thank you for having me. I'll stay on for a few minutes if anybody has more questions.